Programming languages are, well, they're designed for certainty. They're logical, mechanical.
Totally deterministic.
Exactly. 1 + 1 is always 2. But human language, the way we actually think and talk, it's fluid, it's context dependent, and, it's often wonderfully ambiguous. We live in the gray areas.
And that profound difference is, I think, where our deep dive begins today. We're looking at a pretty radical concept.
A next generation programming language.
One designed to natively bridge that exact chasm. And our source material, it's not just some white paper. It's a detailed blueprint, an object model for natural language processing that analyzed over a dozen wildly diverse languages.
From all over the globe, right.
All over. From tonal systems in West Africa to, say, complex inflectional systems in Russia.
So the mission here is to basically reverse engineer human language.
That's it.
Instead of forcing our messy human thoughts into rigid code, we're pulling out the core computational ideas from our grammar, from the way we build meaning, and using that to design a new paradigm.
And the result is a system that can handle both the quantitative data, the numbers we're all used to, and qualitative data.
Things like concepts, abstract states, and context.
Exactly. And the key goal for you, listening, is to see that the linguistic features we sometimes, dismiss as just complexities. Things like a tonal marker changing a word's meaning, or
how some languages can pack a whole sentence into a single verb.
Right. Those aren't just anthropological curiosities, they're functional requirements. And when you model them correctly, they become these incredibly powerful computational tools. They inspire everything from dynamic data types to fuzzy probabilistic logic in this new language.
That is a staggering undertaking. Okay, well, let's unpack this. Starting with the literal foundation. How do you even begin to model language in a way that's flexible enough to inspire code?
Well, to get that flexibility, the designers turned to object-oriented programming. They created what's called a base language class.
Okay.
Think of it as the foundation,
Okay.
the chassis for all language processing. It aggregates all the reusable parts that pretty much every language needs.
And these are the famous NLP tools we hear about, right? Let's maybe clarify what those actually do, because that list can get pretty dense.
For sure. They are the essential tools. So you start with the tokenizer.
Right.
It just breaks down text into usable chunks, words, punctuation, things like that. Then you have the morphological analyzer, which is critical.
Why critical?
Because it understands word structure, how prefixes and suffixes can completely change a word's meaning.
So that's doing way more heavy lifting than like a simple spell check.
Oh, absolutely. Next up is the parser, which handles syntax, the grammar of the sentence itself, figuring out how words relate to each other.
Got it.
Then there's the named entity recognizer, or NER, which finds real-world things like names, places, dates. And crucially, this whole base class is designed to plug into modern AI tools, like language-specific transformer models and word embeddings.
Which you need for deep semantic context.
You absolutely do.
That structure seems, really elegant for reusability. You build the base, and then for a new language, you just extend that class and customize the parts that are different.
Precisely.
But the really hard part, and I guess where the programming inspiration comes from, is in those unique custom requirements for these really diverse languages.
Exactly. The customizations reveal the roadblocks that traditional programming just can't handle. Let's take Yoruba, a prominent language in Nigeria. It's tonal.
Meaning the pitch of your voice matters.
It's everything. The placement of a diacritic, just a little mark over a vowel, can completely change a word's meaning.
So meaning isn't just in the letters, it's in the inflection. Computationally, what does that demand?
It forces the semantic model to be incredibly sensitive to that inflection, to context. And on top of that, Yoruba has agglutinative morphology.
Which means?
Words are often built by chaining together multiple affixes, like building blocks. The analyzer has to deconstruct all those pieces to find the core meaning.
And it's not just grammar.
Not at all. The model also has to interpret cultural context, like complex proverbs. Oh, wait. You're essentially programming intuition, not just a set of rules.
That word construction complexity really dictates how the analyzer has to work. Okay, now let's shift to the Middle East. Arabic seems to have a completely different system for building words.
It does. Arabic is built on this fascinating root and pattern morphology. So imagine most words come from a three-letter root, like KTB, which is related to writing.
Okay.
To get the word for book, writer, or library, you apply different vowel patterns and affixes to that same root. It's a very dynamic, pattern-based system.
So the computational challenge shifts. It goes from chaining parts together, like in Yoruba, to recognizing and transforming patterns across a huge set of possibilities.
Precisely. And that's before you even get to the practical challenges of, say, right-to-left writing or the tokenizer having to handle clitics, these little words that latch on to bigger words and are a nightmare to separate.
Moving east again, Japanese has that immediate visual challenge. The source material calls it the no spaces problem.
That's the fun one. Unlike most Western languages, written Japanese often just doesn't use spaces between words.
So how do you even know where one word ends and the next begins?
You need advanced statistical or AI-based segmentation models just for that first step. And then you have to deal with 3 different writing systems, kanji, hiragana, and katakana, often in the same sentence.
Wow.
So the system has to figure out the right script, perform the segmentation, all before parsing can even think about starting.
Okay, and finally we get to the polysynthetic languages like Navajo and Cherokee. I hear these are the ultimate test for state parsing.
They really are. In these polysynthetic languages, a massive amount of grammatical information gets packed into a single verb.
How massive?
A single word in Navajo can encode the tense, the subject, the object, the way the action was done, the tool used, and the modality. All of it.
Wait, hold on. If one verb holds information that would take, what, 6 or 7 separate words in English, how does that even translate into a computational requirement?
It totally revolutionizes the idea of a function call. Well, if a programming language wants to model that kind of efficiency, it means a single function signature has to dynamically track a dozen different codependent variables and states all at once. This super compressed, complex morphology makes morphological parsing absolutely essential.
And it reveals a need for a language that's better at handling complex, multi-layered state information instead of just simple linear steps.
You got it. It's fascinating how these linguistic oddities, from tones to polysynthetic verbs, are essentially defining the specs for a new kind of logic unit.
And it also ensures that every one of these language models is built to use those sophisticated AI tools we mentioned earlier.
Absolutely. We're fusing ancient grammatical structures with cutting-edge tech. Every specialized class for Russian, German, Arabic, you name it, is built to leverage language-specific transformer models like AraBERT or GermanBERT and specialized word embeddings.
To make sure that deep semantic understanding is baked right in.
Right into the system's core.
Okay, here's where it gets really interesting for me. Taking all those linguistic complexities and actually turning them into programming language features. If the problem is that code is too static, too numbers-focused, how does this new design move beyond 0 and 1?
It moves beyond by natively integrating qualitative concepts. The goal is a language where you can define a state or a concept like trust or quality, and then use that abstract idea in your code just as easily as you'd use the integer 5.
That's feature 1, integrating qualitative and quantitative data.
Exactly.
So let's jump into the first major feature inspired by this. Contextual semantic shifting, which you said comes from tonal languages like Yoruba.
Right. So if a word's meaning can shift based on tone in Yoruba, then a code element's meaning must be able to shift based on its usage context in this new language. We're defining things that are dynamic by nature.
But wait, this is where my engineer brain kicks in. Isn't defining something like mastery a huge philosophical and engineering problem? How does the code decide when, say, learning becomes mastery without massive human input?
That's the challenge. But the linguistic model gives us a bridge. The example in the source shows how you define a qualitative state, let's say learning, that dynamically shifts to mastery when a specific quantitative condition is met.
Like what?
For example, when person.experience 100, the quantitative data acts as the objective trigger for that qualitative shift.
Ah, I see. So the code is adapting the qualitative definition based on hard metrics. I can immediately see applications for that. Think about a car's engine management system.
Go on.
The qualitative state optimal performance could shift to degraded or even critical based on real-time sensor data quantitative things like temperature, pressure, RPMs, your programming states, not just numbers.
Exactly. The system is inherently adaptive. And this leads right into feature 3, granular state representation, which is inspired by Russian verb aspects.
Explain that connection for me, because verb tenses don't immediately sound like they have anything to do with computation.
Well, in Russian, verbs have perfective and imperfective aspects. The imperfective is an action in progress, or continuous. The perfective is an action that's completed with a clear result.
Okay.
The new language uses this exact distinction to model really precise state transitions.
So instead of a simple Boolean, like is done, True, false.
Yeah, you get much more nuance. A task object like write code can transition from in progress, that's the imperfective, to either completed, the perfective, or maybe paused.
Mm.
The system doesn't just track doing versus done, it tracks the kind of completion.
And here's the human part.
And here's the truly human part. Upon a perfective completion, the system can execute qualitative effects on other objects, like setting person.mood satisfied.
So you can assign an emotional or at least a qualitative consequence directly to a computational state change. That's revolutionary for modeling any kind of human scale system.
And if we want to build really complex objects, think about modeling advanced AI architectures. We can turn to German compound words for inspiration. That gives us a flexible composition type system.
Ugh, like the classic Donner Dampfschifffahrtsgesellschaftskapitän, stacking meanings to build a massive word.
Precisely. German has this amazing ability to create these infinitely descriptive compound nouns. We mirror that by supporting a composable, hierarchical data structure in the code.
So you don't need a huge monolithic class.
Right. You build complex types by stacking existing qualitative and quantitative components. You could model a complex type like intelligent machine by simply having it inherit abstract concepts like perception, action, and learning. You're assembling meaning from smaller parts.
That dramatically simplifies how you define a complex system. But since human language is, inherently messy and uncertain, we need a way to handle that. How does the language get past the deterministic 1 + 1 = 2?
By baking that messiness right into the core logic, this language natively includes probabilistic behavior and fuzzy logic.
So it's not always deterministic.
Not at all. It's designed for decision-making under uncertainty. Calculations can return results with, say, confidence scores or likelihoods, modeling the ambiguity you see in natural language or the unpredictable nature of real-world data.
Okay, so we've covered the 4 pillars: dynamic shifting, granular states, flexible composition, and fuzzy logic. Why should this be the language you learn next year? What are the biggest, most practical use cases for a language that marries German grammar with probabilistic execution?
Well, the primary impact is in any area where context and nuance are absolutely critical. So for AI and machine learning, it's a game changer. It's perfect for building adaptive learning systems, especially in NLP, because it can handle the precise numerical data and the fuzzy semantic context at the same time.
And what about for large-scale modeling?
It's essential for multi-agent systems. The language's dynamic relationship modeling, which is inspired by case systems in languages like Arabic or Russian, gives you much better tools for simulating complex, constantly shifting environments.
Like what kind of environment?
Think about modeling social networks or decentralized economic models or even biological ecosystems where relationships are everything and are often ambiguous.
The source material also points to a really ambitious application: revolutionizing operating systems design. How does a language based on verbs help an OS?
The linguistic flexibility could allow an OS to become what they call a universal operating system. It could abstract away complex hardware details in a context-aware way, making cross-platform compatibility much easier.
Less porting work.
Much less. And more importantly, it improves resource management. Instead of fixed rules, the OS would use dynamic, probabilistic decisions based on predicted user needs or system load to allocate CPU and memory. It's an OS that thinks and communicates its resource decisions fluidly.
That sounds like an OS that can anticipate and adapt, not just react. Thinking about other new applications, that context-aware nature seems perfect for complex physical control systems.
Oh, absolutely. Consider adaptive traffic management systems. These could use probabilistic reasoning to factor in unexpected weather or human behavior, adjusting signals in real time far beyond what current algorithms can do.
Or in gaming.
In gaming, it would mean advanced behavioral models, creating NPCs that adapt realistically to player actions using complex probabilistic states. It would make game worlds feel truly alive.
And, of course, the ultimate linguistic application: universal language translators.
Right. Translators that can finally capture nuance, idioms, and cultural context far beyond simple word-for-word translation because they can use that granular state representation to transfer the correct intent.
It's this elegant circle, isn't it?
It really is. We use the language model to fix the translation problem, and then we use the resulting language features to build better computational systems in general.
All these use cases paint a picture of the future. But we have to address the feasibility analysis. Building something this nuanced and flexible sounds like a computational nightmare. What are the really severe hurdles?
There are 2 massive technical hurdles and 1 big human one. The first is the computational complexity risk.
Meaning?
Supporting real-time contextual semantic shifting and probabilistic execution creates a colossal processing overhead. You risk a state explosion. If every variable is dynamically changing based on context, how do you get any speed?
That's the fundamental trade-off, right?
Yeah.
Flexibility for performance. How do they suggest mitigating that?
The recommendation is to move to a hybrid compiled interpreted model. So certain fixed parts are compiled for speed, while the flexible context-aware stuff is interpreted dynamically. And crucially, they stress a reliance on specialized hardware, specifically massive GPU acceleration.
You need it.
Only parallel processing could handle those real-time probabilistic calculations.
And the second technical hurdle is about tooling. If everything is dynamic and probabilistic, how on earth do you debug it?
That is maybe the single greatest challenge for developers. Current debuggers rely on static state. A variable is either 5 or 6. This language needs a specialized debugger for probabilistic execution. You can't just trace fixed states. You have to trace uncertainty. You have to visualize confidence scores and show how a specific context influenced a probabilistic outcome.
So you're building a whole new frontier in software diagnostics.
You have to.
And the final hurdle, the human one, the adoption risk.
Precisely. The learning curve is steep. You're asking developers used to rigid paradigms to embrace linguistic abstraction.
So how do you mitigate that?
The source suggests offering a familiar front end, maybe a Python-like syntax option at first, to ease people in.
Yeah.
And that has to be paired with a massive focused investment in really sophisticated tooling and interactive documentation. You have to make the complex feel intuitive.
We have completed this deep dive into a paradigm that turns grammar rules into computational logic. The mission is clear: to create code that thinks more like a human, bridging that gap between qualitative concepts and quantitative data.
And while the promise of intuitive, context-aware programming is incredibly compelling, the fundamental long-term challenge is still defining the formal semantics of a language this flexible. You need that expressiveness, but you also need to ground its behavior in complex mathematical rigor, maybe models from category theory or type theory.
Why is that so important?
Because that's the ultimate test. You have to ensure that all this linguistic flexibility doesn't result in unpredictable or ambiguous execution, where the code works differently depending on how you interpret the context.
So what does this all mean? It means the line between a compiler that executes rules and an interpreter that understands context. It might soon become as fluid as human conversation. Think about that the next time you write a line of code.